All right, so we already talked about constant functions, which are degree 0, linear functions are degree 1, and now quadratic functions are degree 2 because the highest exponent here is 2. They're of the form ax squared plus bx plus c. When the function is written in this form, this is called standard form. And the caveat here is that a can be any real number except for 0. Of course, you can manipulate this expression and write your quadratic in any form. But another really helpful form is f of x equals a times the quantity x minus h squared plus k. When the quadratic is written in this form, it's called vertex form. Because as we will see, if it's written in this form, you can easily tell what the vertex is. Alright, so what I want to do is take a look at the graph of these functions and compare them. So let's take a look on Desmos. I have here the graph of y equals x squared, which you might be familiar with. It's a parabola. It looks like a curve. It's got a vertex here right at the origin. That's the lowest minimum point on the graph. Now let's look at the graph of y equals x squared plus 3. Okay, so what you'll notice is it's like the same exact graph, just shifted. The vertex has been shifted up 3 units. Alright, let's undo that graph. Let's take a look at x minus 2 quantity squared. Looks like the same exact picture, only the graph has been shifted to the right 2 units. Okay, so with that being said, I will graph one more. I'm going to combine these two ideas. So what if I wanted to graph a parabola whose vertex was 2 units to the right and 3 units up? I'm going to guess that if I do x minus 2 and square that and then add 3 on the outside of the function, that gives me a parabola that looks exactly the same, where the vertex is now at 2, 3. So when your quadratic is written in this form, it's vertex form, and you can see that 2 is the x-coordinate of the vertex, and the 3 on the outside here is the y-coordinate of the vertex. Alright, so just a couple other things to notice. What if we multiplied the outside of the function by 2? What you get is the same parabola with the same vertex, but just narrower than the original. And I'm going to guess that if I look at y equals 1/2 x squared, it'll be the same parabola, same vertex, but just wider. Yep. So if you take the x squared function, multiply by a number bigger than 2, it's narrower. Multiply by a number bigger than 1, it's narrower. Multiply by a fraction less than 1, and it becomes wider. And then the last thing to look at is what if you negate the function? Comparing y equals x squared to y equals negative x squared. That flips the parabola down. So it takes all of those positive output values and makes them negative. Alright, so all parabolas can be constructed this way. And again, you can either look at parabolas in standard form and try to manipulate them from there, or if your quadratic happens to be in vertex form, then you can get a little bit more information. In particular, if it's in vertex form, then your vertex will be h, k. So again, noticing here, if it's written in vertex form, you know what the vertex is. Notice that it's the x-coordinate of the vertex will be the opposite sign of this number. So if it was like x minus 2 squared, the x-coordinate would be 2. If it was x plus 2 squared, the x-coordinate would be negative 2. So it's always the opposite because there's a minus here. And then if your quadratic's written in standard form, you can actually quickly, not as quickly, you can't just see the vertex, but you can quickly find the vertex with the formula x is negative b over 2a. This formula comes from, you can get it from the quadratic formula. It appears there as a result of completing the square, which is, I think there's a video about completing the square in the review section. All right, so then that'll give you the x-coordinate of the vertex, and then whatever this number is, what you do is you plug it back into the function to see the corresponding y-coordinate. All right, next will come some examples where we find the vertices and other important properties of these parabolas.